We've looked at one way to determine a rate law using experimental data. I want to present another way, although this will be a very brief introduction to a graphical analysis of the time evolution of the concentrations of a reactant. So our learning goal is how to determine the rate law from this time evolution data. Now, one thing I'll notice is that it's difficult to tell first and second order reactions apart. They both decay to zero. The second order reaction decays over a little bit longer time, but unless we're measuring this for a very long time, it'd be hard to tell the difference between them. The other thing I would notice is that experimental data often has measurement error, so it doesn't lie precisely on the curve that we think it should lie on. Now, here's an example, where we might have a series of data points where we have concentrations that occur at different times, and the curve is meant to represent how the data is actually supposed to lie, and you can see that some of the data points don't exactly lie on that line. There's a little bit of experimental error in this. Now, the whole idea behind the graphical analysis method is that we want to try out a theory. That is to say, our theory might be that it's a first order reaction, or our theory might be that it's a second order reaction. And we want to see if we can recast the data in such a way that we can convert this to a linear graph. The reason we want to make it a linear graph is because we have very good, robust statistical methods for fitting data to a line. And so the whole idea is that if we can make our theory look like a linear graph and then take our real data, manipulate the data to fit that theory, if it fits a line, then we're going to suppose that the data actually represents that order of a reaction. So we need to figure out exactly how we do that depending upon what we're supposing the reaction order to be. So what we want to do is we want to graph a function of the concentration versus time. Now, if it's a zeroth order reaction, the reactants should already be in some sort of linear order. We saw that earlier with the integrated rate law for a zeroth order reaction. It actually is a line with negative slope. So in that case, we don't really have to do anything. The data itself should approximate a line. What if it's a first order reaction? Well, in this case, we know it's not a line, the actual data, and we have this, if we are supposing that it's a first order equation, then it should be following a rate law that looks something like this. A at time t is equal to a at 0 times e to the minus kt. Well, the way we can convert this into a linear type function is by taking the natural logarithm of both sides. And I'm not going to go through the mathematical details of this, but the result would be that I would have the log of the concentration at time t is equal to the initial concentration log minus kt. So now this is a linear function in time. What I'm looking for is something that's got just k times time in this equation, and it's related to a function of the concentration of the reactant A. If it's a second order reaction, our integrated rate law is a little bit more complicated. It's 1 over A at time t is equal to 1 over A at time 0 plus kt. Now this also resembles a linear form, but it's only linear if we're plotting 1 over the concentration versus time. All right, in that case, if we're say plotting y versus x, our y would be the 1 over the concentration and our x would be the time. So let's see how this might look. I'm just going to show you a brief example. We're not going to work through this. An example involving the decomposition of hydrogen peroxide. So the real data might look like this. The times are listed in the first column and the concentrations are listed in the second column. And if you plotted out those concentrations as a function of time, it would look like the curve shown on the right, the large graph on the right. Now, if I want to test this for a first order, then I would take the logarithm of each of those data points, and I've done that in the third column. So the logarithm of 1 is 0, the logarithm of 0.91 is negative 0.105, and so forth. And I would then plot all of those points as a function of time. Okay, when I do that, I can then see if it fits a line. And if it fits a line, then I can make the assumption that perhaps this is a first order reaction. The other thing I could do, though, is I could test to see if it's a second order reaction. I would take each of the data points and take 1 over that data point. So if it's 1, then it's 1 over 1 is 1. If it's 0.91, 1 over 0.91 is 1.10, and so forth. And so the last column in the table is showing me what happens if I manipulate the data to make it look like 1 over that. So I would then plot that versus time. All right, and then I would test both of those two possibilities, the log of the concentration versus time and 1 over the concentration versus time, and see which fit a better line. In this particular case, it's the log of the data of the concentrations that fits the better line, so we would deduce that this is a first-order reaction. But you'll get a chance to do some of this analysis later on in Lab 4.